So the question we want to start with is the following. How do we solve the equation x squared plus 1 is equal to 0? So from chapter 1, we know that a solution to an equation is a value of x that when we substitute it into the equation, it makes the statement true. Well, let's analyze this, because for real numbers, there are exactly 3 types of real numbers. And we have positive numbers, we have negative numbers, and we have 0. And those are the 3 possibilities. So that means if there's a solution to this equation, it must be one of those 3 things. X either has to be positive, x has to be negative, or potentially x could be 0. Well, let's evaluate each of those 3 cases. So if x is less than, or if x is positive, that is, we have x is greater than 0, we would have the following. So then x squared would be the same as x times x, but since x is positive, we know that that would be a positive times a positive, and if you multiply a positive number by a positive number, we know the result would also have to be a positive number. So now if we check that in our equation, x squared being a positive number, a positive number plus 1 is going to be another positive number, which can't be the same as 0, right? So this would show no matter what x we pick, a positive x could never be a solution to that equation. We're like, well, that's okay. So let's try a different one. Well, if x can't be positive, well then maybe x is negative. Well, if x is a negative number, it's less than 0, we still have x squared, which would be x times x, but this time it would be a negative times a negative. But once again, a negative times a negative would yield a positive product. And we're going to have the same issue that we had before. If we have x squared as positive, a positive number plus 1 is still positive, which can't be the number 0. So this is also not a solution. So the equation x squared plus 1 equals 0, x can't be negative, x can't be positive, so what's the only possible choice that's left? 0. But we can check that one directly. If x is 0, we just plug that into our equation directly. So x squared plus 1 would be 0 squared plus 1, which is 1, which is not 0. And we see that for this equation then, we have the following predicament. There is no real number x such that x squared plus 1 is equal to 0. It's just, we checked all the possible cases, which was x was positive, x was negative, and x was 0, and none of them were a solution to this equation. So we're going to do something that mathematicians and scientists do all the time. We need to expand our number system. So when we do so, we are going to define, and this is a definition, a new number and it's going to have symbol I, and we write it as a lowercase I, to be the number with the property that I squared is equal to -1. So this is a new number that has a property that no real number has, because as we saw, if you multiply a positive by a positive, it's positive, and if you multiply a negative by a negative, it is also positive, and if you multiply 0 by 0, you get 0. So there is no real number that has the property that when you multiply it by itself, you get a negative number. So this is the only number with the above property. So the number I is called the imaginary unit. And that's really a misnomer, and we'll talk about why they called it an imaginary number a little bit later on today. But I is called the imaginary unit. We'll also note that I is a solution to x squared plus 1 is equal to 0. Because if I is a number with the property that I squared equals -1, we can check then that I squared plus 1, well, I squared is -1, so that's -1 plus 1, which equals 0. So indeed, it is a solution to that equation. So I is a new number called the imaginary unit, and it has a unique property, and it's the only number with this property, that when you multiply it by itself, it is equal to -1. There is another equivalent way to talk about this. So since I squared is equal to -1, if we take the square root of both sides, we would have the square root of I squared is equal to the square root of -1. But a square and a square root undo each other, so we would get I is equal to the square root of -1. Some textbooks actually use this as the definition and use it to derive I squared equals -1. They are just two different ways to define the same thing. I want everyone to grab their graphing calculator. Let's go ahead and turn this thing on. And if we go second and our squared button to get our square root, and then we come down here and we go -1, and we press enter, we should get something that looks like this. We should get our calculator says non-real answer, and then it tells us that that's an error. Well, we know that the square root of -1 isn't a real number. In fact, it's I, which is the imaginary unit. It turns out our graphing device will do complex arithmetic, as we'll see, or imaginary numbers. But we need to change a setting on our calculator. So I need everyone to press the mode key on their calculator, and you'll notice down here, our calculator is in what is called real mode right now. We want to go down to this line and change it from real to A plus BI. We'll talk about what A plus BI is in just a minute, but go ahead, arrow over to A plus BI, and press enter, and that is going to change our calculator from real mode into imaginary or complex mode. After you're done, go ahead and press your clear key or second quit to get back to your home screen. And then let's try this again. Let's go second square root and then go -1. And when we do it on our calculator this time, what does our calculator tell us the square root of -1 is equal to? Well, we should get the imaginary unit I, which is what we thought it should be. So we can also find the number I on our graphing calculator. If we look down in the bottom row on our decimal point key, the secondary function is our imaginary unit I. So if I go second and my decimal point key, that puts the I on, and now let's go ahead and square it. If I go I squared, I get that the solution, as we know by definition, I squared is equal to -1. Okay, so we'll talk more about using our graphing calculator in a minute, but that's how we can use it to at least get the number I and do some very simple computations with it. We need another definition, and then we'll come back to this in just a minute. So our next definition is of a complex number. Has the form A plus BI, where the I is the imaginary unit. So where A and B are real numbers, and I is the imaginary unit. So let's talk a little bit about the anatomy of a complex number. So a complex number, as written above, has the form A plus BI. A is going to be called the real part. So that's the part that's not connected to the I. And the part that is connected to the I is called the imaginary part. So a complex number has two parts. It has a real part and it has an imaginary part. When we write complex numbers, we always write them with the real part first and the imaginary part second. The great thing about complex numbers is I behaves just like a variable, with one exception. We must use I squared equals -1 to simplify powers of I. So what this means is when we are working on complex numbers or working with them, the I is going to behave just like an X, with one exception. Pardon me. If we ever have an I squared, we are going to replace it with -1. All right. So let's finally, after all those definitions, take a look at example 1. So example 1 says simplify this. Well, I'm going to simplify this just like I would if I was an x. I distribute my minus sign into my parentheses. So I get negative 5 plus 6i minus 6 minus 9i. And then I have my like terms. So I have my negative 5 and my negative 6, which would give me negative 5 take away 6 is negative 11. And then I have my other like terms. I have 6i take away 9i. So 6 take away 9 is negative 3i. And that would be my solution. So this is what I was saying when I behaves just like a variable. We're going to gather it up just like we would with any like terms. The only thing that's going to be a little bit different is if we have a power of I, e.g. I squared, we must replace it with a negative 1 and then just keep simplifying. So in the interest of full disclosure, this one was really easy to do by hand, but if you felt so compelled, you could type this into your calculator now that we've put this into complex mode. So I could type it in exactly how it looks. So parenthesis, negative 5 plus 6, and my I, remember, is my secondary function on my decimal point key. Close my parentheses, minus, open new parentheses, 6 plus 9i, and then I close my parentheses, and if I hit enter, my calculator gives me exactly the same thing we got by hand. And I'll be honest, in my personal opinion, for addition and subtraction, I think it takes longer to type it in the calculator than to just collect your like terms. But either way you wish to do it is fine, right? You're going to get exactly the same thing, negative 11 minus 3i. And it's also worth noting our calculator follows the convention where it does the real part first and the imaginary part second. So when we're writing complex numbers, it's always real part, then the imaginary part. Okay, so I'm going to do a few more of these and then we'll talk about our calculator a little bit. So let's go to example number 2, and then I'll let you guys work on a couple of you tries. So our next one says simplify negative 3 plus 5i squared. Well, we need to remember that when we square something, what that really means is to multiply it by itself. So if we write it out this way, what we're really doing is it wants us to distribute or quote-unquote FOIL this thing out. So if we use our distributive law and distribute the minus 3 into our parentheses, negative 3 times negative 3 is positive 9. Negative 3 times 5i is negative 15i. And then we distribute the 5i into our parentheses. 5i times negative 3 is negative 15i. And 5i times 5i is going to be positive 25, and then I times I is I squared. So now we need to simplify this up a bit. So we have some like terms here, negative 15i and negative 15i. So I have 9 minus 30i plus 25. But then what is I squared the same as? Well, we know that I squared by definition is negative 1. So our I squared is going to get replaced with a negative 1. So I have 25 times negative 1. So I get 9 minus 30i minus 25. So then 9 take away 25 gives me negative 16 take away 30i. And notice I wrote it as the real part minus the imaginary part. But once again, I did all this arithmetic by hand, and there's no reason we have to. If I just grab my graphing calculator, I have negative 3 plus 5i, close my parentheses, and then I square it. And my graphing calculator agrees with me. The solution was negative 16 minus 30i. Right? So our calculator, as long as we put it in complex mode, can do complex arithmetic for us. We're going to talk about one exception because a little bit later on, because the TI graphing calculator has a problem. All right, so once again, to simplify U try 1, we just collect our like terms. So 3 minus 7 is going to give us negative 4. Negative 6i plus 4i is going to give us negative 2i. So we get negative 4 minus 2i. Our next one, we distribute into our parentheses. So 1 times 2 is 2. 1 times 4i is positive 4i. And we distribute our negative 2i in. Negative 2i times 2 is negative 4i. And negative 2i times negative 4, or positive 4i, gives us negative 8. And I times I is I squared. And we don't want to forget I squared is the same as negative 1. So that gives us 2. Positive 4i and negative 4i reduce out. Minus 8. And I squared is negative 1. So a negative negative makes a positive. Because a negative times a negative is positive. So 2 plus 8 gives us 10. And if you plug that into your graphing device, for both of them, you should have gotten exactly the same thing. So we need another definition now, which is called the conjugate. The conjugate of the complex number a plus bi is a minus bi. That is, we change the sign on the imaginary part. So, moreover, the product of a complex number and its conjugate is always a real number. So if we look at that, if we had a plus bi, its conjugate would be a minus bi. And if we were to distribute this out, we would distribute our a into our parentheses. A times a is a squared. A times negative bi is negative abi. And then if we distribute the bi in, bi times a is positive abi. And bi times negative bi is negative b squared I squared. And we notice that we have a negative abi and a positive abi, so they're equal but opposite, and they're going to add up to 0 or cancel out. And our I squared is the same as negative 1. So we end up with a squared minus b squared times negative 1, which is just a squared plus b squared. So it tells us then that if we multiply a complex number by its conjugate, we will always get a pure real number. Notice all of the i's reduced out, and it will always be the real part squared plus the imaginary part squared. So and that will happen 100% of the time. So it's worth noting that we could have seen that. We actually saw this in U try number 2, but it's a little tricky. So we had 1 minus 2i times 2 plus 4i. And you're probably saying, well, Professor Peterson, those are not conjugates. But if we look at this, it actually has a GCF of 2. If I were to factor a 2 out of that, so I factor out a 2, I have my 1 minus 2i, and then I have 1 plus 2i. These two guys are indeed conjugates. And my real part is 1, and my imaginary part is 2. So according to our formula here, we would have 2 times the real part squared plus the imaginary part squared. So 1 squared plus 2 squared, which is 2 times 1 plus 4, which is 2 times 5, which equals 10. Same thing we got above. It's just a different way to do that, but complex conjugates always have this property. So it's a little bit interesting that it works out that way. So this leads us into our next example, and you're probably thinking, well, what in the heck does that have to do with example number 3? So for example number 3, we are asked to simplify this. So we're asked to do division. The thing is, we may not know how to divide by the imaginary unit, which we don't. So to do division by hand, we multiply the numerator and denominator by the conjugate of the denominator. So we would have 5 minus 3i all over 3 minus 4i, and we would have to multiply the top and the bottom by the conjugate of the denominator. So we change the sign on the imaginary part. So instead of 3 minus 4i, it would be 3 plus 4i over 3 plus 4i. And then we would have to multiply all of this out. So 5 times 3 is 15. 5 times 4i is 20i. Negative 3i times 3 is negative 9i. And negative 3i times positive 4i is negative 12i squared. And then in the denominator, we would have 3 squared plus 4 squared, because we multiplied by the conjugate. If you FOIL it out, you'll see you get the same thing. So then in our numerator, we have 15. 20i minus 9i is positive 11i. And negative 12i squared changes to positive 12 because I squared is negative 1. Negative 12 times negative 1 is positive 12. And then in our denominator, we get 9 plus 16. 3 squared is 9, 4 squared is 16. So finally, we get 27 plus 11i all over 25. And then to make it in the form a plus bi, we do term-wise division. So we would write it as 27 over 25 plus 11 over 25 by putting the denominator over each of them. And you're probably thinking, well, Professor Peterson, why didn't you just type it into your calculator? Well, good question. Let's go ahead and try and see what happens. So I want everyone to grab their graphing device. Let's go ahead and do this. So we grab our fraction by going alpha y equals. I am not in the right place. Alpha y equals, and we type it in, 5 minus 3i over 3 minus 4i. And then I'm going to go ahead and press enter on my calculator. And my calculator tells me this. It says error data type. So some of you may get this error. Essentially, if you have a TI graphing calculator that looks like the emulator that I'm using, you're going to get this error. If you have one of the color versions, so the C or the CE, it worked just fine and gave you the answer, right? So for those of us that have the TI-84 Silver, the Plus, or just the regular TI-84, unfortunately they don't update it beyond this. We have to type it in a little bit differently. So for us, instead of being able to use this notation for TI-84, 84 Plus, or 84 Silver, or Silver Plus. So basically, any black and white. If you have a color model, it works. We have to type it in numerator divided by denominator. And then we're going to press our math key and choose fraction. So for us to do that problem, we would type it in this way. We go parenthesis, and we put our numerator, so 5 minus 3i, close our parenthesis, we press our divide key, parenthesis, 3 minus 4i, close our parenthesis, we press our math key, and we choose choice number 1 that says fraction, and we press enter, and we should end up with this. So we can get our calculator to do this complex arithmetic. We just have to ask nicely. So if we ask in this fashion, it will indeed give us the same thing. And let's just double check our work that we did by hand. 27 over 25 plus 11 over 25i, and indeed we got exactly the same thing, right? So just be aware that we have to ask our calculator in a little bit nicer of a way. All right, so to resolve this one, it's calculator food, so let's go ahead and just type that thing in and see what we get. 6 plus 13i divided by 5 plus 12i. Math, fraction, and we get 186 over 169 minus 7 over 169i. for our solution. All right, so the next example we want to talk about, example 4, we need to write a couple of things down before we actually start working on it. So for powers of I, like I to the n, we must be careful with the TI graphing calculator. So the reason for this is there is a programming error in that calculator, and if you type in large powers of I, it will not give you the correct answer. So let's take a look at a couple of things. So if we have I to the 0 power, anything to the 0 power will always be 1. I to the first power is just going to be I. By definition, I squared is -1. I cubed, well, I cubed by our exponent laws is really just I squared times I, so that's -1 times I, which is -I. And I to the fourth, using our exponent laws, is the same as I squared times I squared, which is -1 times -1, which is +1. And we'll notice that we loop back to where we started. So then the pattern starts all over again. I to the fifth is going to be the same as I to the sixth is going to be -1, I to the seventh is going to be -I, and I to the eighth is equal to +1 again, and then the pattern just repeats. So I to the ninth would then be the same as I, and this continues forever. So if we keep multiplying I by itself, we know that there are only 4 possible answers. 1, I, -1, or -I. Well, now comes what I was talking about on our graphing calculator. If I go I, and I raise it to the 100th power, well, that one worked. So I have to pick one that did. Let's go to the 101st power. I get something that is not just I, 1, -1, or I. So our graphing calculator gives us something, but it is not quite the correct answer. We'll talk about what's wrong with that in a second. But for right now, what we want to use is the following. We notice that this pattern, every 4 factors of I is equal to 1. So since groups of 4 factors of I equal -1 or equal 1, what we have in symbols is that I to the fourth equals 1, we can use the following. To calculate large powers of I, we divide so I to the n, we divide n by 4 to find the remainder. R. Then we have the following. I to the n is the same as I raised to the r. All right. So let's take a look at example 4. So if we want to calculate I to the 127th power, what our thing says is we are going to take our exponent, 127, and we're going to divide it by 4. So 4 goes into 12 3 times. That gives us 12. We subtract, we get 0. Bring down our 7. 4 goes into 7 once. 1 times 4 is 4. 7 minus 4 is 3. 4 no longer goes into 3, so that gives us our remainder. So I to the 127th power is the same as I to the third, because this is our remainder. And then I to the third power, we know, is negative I. So that would be our solution to that problem. If we check this on our graphing device, we get I to the 127 we notice our calculator doesn't give us quite the correct answer. But we do notice the correct answer is negative I, which is right here. But we get this part that's left over right here. So then the question is, well, what is this negative 2.3 e to the negative 12? Well, this is our calculator's way of saying scientific notation. So this is really negative 2.3 times 10 to the negative 12th power, which would mean I need to move my decimal to the left 12 places. So it's negative 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 3. So that's actually a really, really small number, right? So the problem with this is this really shouldn't be here. It should be 0. That's round off error because they programmed our calculator really using a sloppy algorithm. So for those of you that are into computer science, they have a numerical leak is what's happening. So we have to be careful when using our calculator. So if we do that, we really need to discard any small error. So in this case, if we look at it, it's 0.000000. That's really small. That's not what we want. The actual answer is there. We just have to be careful. So they're pretty easy to just do by hand, but if you want to use your calculator, it's possible. It's just not very convenient because of this round off error stuff that we end up with. So just keep that in mind. All right. So it's now your turn to go ahead and do